The pediatrics unit at Carver Hospital has 24 beds. The number of patients needing a bed at any given time is normally distributed with an average of 19.2 and standard deviation of 2.5. So again, we have a normally distributed distribution. 19.2 beds is the average and the standard deviation is 2.5. Questions are, what is the probability that the number of patients needing beds will exceed the pediatric unit's capacity? The capacity is 24. So what's the probability that the number of beds needed, the random variable, exceeds 24 beds? Okay, so I need to calculate the probability that x is greater than 24. 24, let's go ahead and put it in the distribution. And I want the probability that x is greater than 24, which is going to be the area under the distribution above the interval. Now to get that, I'm going to need to find the z-score of 24. So 24, how many standard deviations is it from 19.2? So I'm dividing by 2.5, and I get 1.92. It is almost 2 standard deviations to the right of the center of this distribution. Now the table always reads to the left, so I'm going to look up the 1.92. I'm on the upper end, so I'm looking at the positive z-score table, and down into row 1.9 and over to column 0.02 gives me a 0.9726. And so to get my answer, remember the probability under the density function totals 1. So I'm going to have to subtract the 0.9726 from 1 to get 0.0274, or approximately 2.7%. So the probability that the capacity will be exceeded and that they're going to not have beds for people, there's a 2.7% probability of that happening. And again, it's the area under the density function above the interval. And in this case, our table always reads to the left, so I need to subtract the table value from 1 to get what I needed. Okay, question B. 90% of the time, at least how many beds will be needed? Okay, for that one, we're actually given a percentage, and what's going to answer that is the endpoint of an interval. So I'm going to kind of work backwards, in a sense, to the problem I just did. 90% of the time, at least how many beds will be needed? Okay, very carefully thinking of what that would mean. 90% of the time, at least how many beds would be needed? So I'm talking about this part of the distribution. Again, the average is 19.2. Standard deviation is 2.5. Now I have a z-score formula that relates everything here, but I don't have the x and I don't have its z-value yet. But I know that I'm going to be subtracting the average from x and dividing by the standard deviation. What I need is the z-value for x. The table is going to read to the left, and I know that area's got to be 0.10 because there's 90% above the x. It says 90% of the time, at least how many beds will be needed? So 90 is in the upper part of this distribution, and I'm getting the lower part is 10%, and that's what I need to go to the table because the table reads to the left. So looking up here in the table, Now, let's see. I noticed down in row negative 1.2, if you look across that row, I get a 1.020, and then I get a 0.1003, and then I get a 0.985, and those are in columns 0.07, 0.08, and 0.09. So as close as I can get to the lower area being 0.1, that's going to give my z value at a negative 1.28, right? This 0.0 or 0.1003 is as close as I can get. So my z-score will be a negative 1.28, and that would be equal to x minus 19.2 divided by 2.5. And then I would take negative 1.28, multiply both sides by 2.5, so it cancels on the right, and then I'm going to add 19.2. So I'm just solving the equation for x, and then x turns out to be 16. So I can say 90% of the time, at least 16 beds will be needed. Now again, that's a very careful understanding of what the problem is wanting. 90% of the time, at least how many beds will be needed. In other words, how many beds or more will be needed 90% of the time. So the 90 is in the upper end of the distribution, and the x that we're looking for is on the lower end. Now, C, 90% of the time, at least how many beds will be empty? So we are going to use the same distribution. Well, actually, it's the only distribution we have. And remember that the random variable here is how many beds are needed. So right away, the question is a little different. 90% of the time, at least how many beds will be empty or not needed? 90% of the time, at least how many beds will be empty translates into 90% of the time, at most how many beds will be needed. So we are going to start here. 90% of the time, at most how many beds will be needed. So that would take us to an upper end. 90% of the time, at most how many beds would be needed. And again, compare that to the question in B. This is going to be a 90% on the lower part of the distribution. And I'm going to be able to look up the table value for that. For a 90%, let's see, I find that one in row 1.2, and then I notice in the values in that row I get a 0.8980, a 0.8997, and a 0.9015. And those are in columns 0.07, 0.08, and 0.09. Now, as close as I can get to 90% is the 0.8997. So in my z-score formula, I'm going to have row 1.2 and column 0.08. I'm going to have a positive 1.28 equal to x, subtract my 19.2, divided by 2.5. And then when I solve for x, I'll have 1.28 times 2.5. And again, add the 19.2. And x turns out to be 22.4. So 90% of the time, I will need at most 22.4 beds. So 90% of the time, at least how many beds will be empty? Well, I would take the 22.4 away from 24 and get 1.6. So the answer to the problem is at least, if you want to be practical about it, at least one bed. At least one bed will be empty 90% of the time. That means one or more beds will be empty. But 90% of the time, at least one bed will be empty. And because the random variable is the number of beds needed, I had to try to translate that into the context of the problem by solving first 90% of the time at most how many beds will be needed. Well, 90% of the time at most 22.4 beds will be needed. So 90% of the time, since we only have 24 beds, at least 1.6 beds will be empty, or practically one bed. At least one bed will be empty. That part C is a little tricky, so you might have to think about that a little while. The terms, the phrases at least and at most and working with the distributions can be a little confusing. You just want to be careful. Now, comparing B and C, notice that one problem is on the lower end of the distribution, and the other problem, C, is symmetrically the same distance on the upper end of the distribution. And again, notice that our z-scores are symmetrically opposites in a sense. I'm negative 1.28 on the lower end with 10%, and I'm positive 1.28 on the upper end with that 90%.